Hey guys, so my presentation today is on the computation of eigenfunctions on various domains. To begin, I wanted to introduce a few fundamental ideas. The first is the Laplacian operator. So this is an operator that takes in a function and spits out a new function. Just like taking the derivative of a function, you get a new function. And this operates on functions in Euclidean space, and it's defined as the sum of the second partial derivatives of the function. This is really common in many fundamental equations of physics, and a really common problem is finding the eigenvalues and eigenfunctions of this operator. The next idea I wanted to introduce is the Laplace-Beltrami operator. So just how the Laplacian operates on functions in Euclidean space, the Laplace-Beltrami operator is a generalized notion of the Laplacian and operates on functions of abstract spaces. So, for instance, the Laplacian can be used for some physical equations involving a domain on a plane, but the Laplace-Beltrami operator can be used to describe different waves on the surface of maybe a sphere or surface of a torus or surface of any sort of manifold we want to describe. And this generalized notion of the Laplacian allows us to solve for these different physical equations, but on more generalized surfaces than just a plane or 3D space or whatever. So a really significant application of this is in quantum mechanics. And so brief overview of quantum mechanics. Basically, in classical mechanics, determining an object's location is really precise. But in quantum mechanics, we can only know the probability that a particle can be located in some region. And this probability density is described by a wave function, and a more physical, intuitive interpretation of a wave function is a vibrating violin string or vibrating drum membrane. These problems physically are very different, but mathematically they're very similar. And so, just like how a violin string is fixed on the endpoints, or a drum membrane is fixed along the boundary, similarly, the wave functions used in quantum mechanics are fixed along the boundaries of domains. And so, just how when you pluck a violin string, it gives you a very specific pitch and very specific discrete set of overtones, these harmonics. And if you hit a drum, it has a very specific pitch and a very specific set of discrete overtones. In quantum mechanics, the analogous value is the allowed energy values within a domain, for a particle within a domain. So this wave function is described as solutions of the Schrödinger equation, and the eigenvalues are the allowed energy states of a particle. The eigenfunctions are the allowed wave functions. So in the Schrödinger equation, we have this function v, and so for a free stationary particle, the value of v is 0 within our domain. Just like if a particle is trapped inside some region, the potential is 0 inside that region and infinite outside of that region. We call that an infinite potential well. And like I said before, this Schrödinger equation is mathematically equivalent to the Helmholtz equation that we can use to describe a vibrating membrane. With Dirichlet boundary conditions, this means the value of the function is fixed at 0 along the boundary of the domain. And this is what gives us these discrete energy values. Here's just the procedure, the substitutions to see that those are equivalent. So now I want to introduce this method for solving for our eigenfunctions. There's two main concepts behind this method. The first is we can pick any arbitrary region, any arbitrary planar domain, and we want to embed it inside a rectangle. And the second main concept is we want to substitute our v value in region 2, this region between our domain and the rectangle, for some large finite value instead of infinity. And these two points will allow us to numerically calculate our eigenfunctions for any planar domain. So the reason we want to embed it into a rectangle is because the solutions for the Helmholtz equation in a rectangle are known, and they're of this form. We're going to use these functions as our basis functions. And we will find our eigenfunctions to be a linear combination of these basis functions. And we just need to determine the coefficients. And so to determine those coefficients, we decided to choose a large finite value for our potential energy inside region 2. And we end up with our Hamiltonian operator in the Schrödinger equation to be expanded out to this form. And because we've chosen a finite value, we can evaluate it, a finite value for v outside of our domain. We can evaluate this, and essentially we just perform a lot of calculations of these integrals for our elements of this matrix. And I mean, depending on the integrals, sometimes we can do it analytically, sometimes we have to do it numerically. But either way, we come up with our what we call our Hamiltonian matrix. And essentially, once we get this matrix, because the value of v inside our domain is 0, this matrix is essentially a matrix representation of our Laplacian. And then because we have a matrix representation of the Laplacian, we can easily numerically calculate the eigenvectors and eigenvalues of this matrix to obtain our numerically approximated eigenfunctions. And essentially, we get these eigenvectors whose elements, so for the first eigenvector, it corresponds to the first eigenvalue, and the elements of the first eigenvector are the coefficients for our linear combination of our basis functions. And so essentially we just solve the eigenvalue problem, and then from that we obtain eigenvectors and eigenvalues associated with our Hamiltonian operator, which in this case is equivalent to the Laplacian operator with some change of units. And by using this method, here I've shown some plots of our numerically calculated eigenfunctions. Here's a circle, here's a density plot of these functions. This is the first 12. Here they are for quarter circle domain. Here they are for various triangles. And I won't get into this too much, but I mean, I calculated these for lots of domains, lots of different domains. I don't have them all here in this presentation, but one thing that I've found really interesting to explore is these, as we have different triangles, as we manipulate the triangles, how do these nodal lines, change? So here, it cuts it in half vertically, but as for this tall isosceles triangle, the nodal line cuts it horizontally. So we can see these different patterns emerge, and this bifurcation as we change these different parameters of our domain. Another interesting pattern is for these different ring domains, depending on the shape of the hole inside the ring or the size, we end up with these different patterns. And a lot of the time we end up with multiple eigenvalues. For instance, the first eigenvalue of this ring domain is a multiple with multiplicity 4. However, for this wide ring, the first eigenvalue is not a multiple eigenvalue, but the second one is, because the resulting wave function is equivalent up to some symmetry. And so there are a lot of a variety of different patterns and more things to analyze about wave functions. And this method provides a very straightforward approach to evaluating these patterns. Here we have some higher energy states of different triangle domains. I've compared the energy values for different triangles and normalizing the energy units to the area of the triangle. We can compare these energy values differ from triangle to triangle. Here, this is pretty important. So I wanted to calculate how accurate this approach is. And so in order to do that, I needed to compare my data with an analytical solution for these eigenvalues. And so in my research, I found there is an analytical approach to solving for the eigenvalues of the Laplacian in an equilateral triangle domain. And as you can see, it almost matches precisely with my numerical solutions. And here is a percent error. It stays around 0.2% error. And I mean, I'm still researching more ways to get that error down. So the next part of my research is extension of this expansion method, this method for solving for the eigenfunction of Laplacian, to solving for the eigenfunctions of Laplace-Beltrami operator on more general surfaces. And essentially, I discovered that as long as we have some domain where the eigenfunctions are known, we can embed any arbitrary domain inside that known domain and use the expansion method to solve for eigenfunctions of this arbitrary domain. Just like how we embedded an arbitrary planar region into a rectangle, we can do the same for embedding some shape on a sphere, for example, because we know the eigenfunctions for a sphere are the spherical harmonics, and we can use the spherical harmonics as our basis functions, and we can pick some arbitrary region on a sphere and solve using the method I just described. So for example, this here I'm just detailing how we index, because for the sphere harmonics we have two indices, and it's not as straightforward as indices of a matrix, because the L index runs from non-negative integers, and the M index runs along negative L to positive L. So here's just a bijection I've used to be able to map these basis functions to a vector. And so, for example, if we wanted to solve for the eigenfunction of an octant of a sphere, we can use the expansion method, this extension of the expansion method. And we just need to determine the coefficients of our linear combination of the sphere harmonics. So here, this is the matrix representation of the Hamiltonian operator in the Hilbert space, and using our sphere harmonics as the basis functions, We expand this out, and we do a change of basis to accommodate for spherical coordinates. We evaluate the Laplace-Beltrami operator on our basis functions. We get this term, and then we have our properly chosen large finite value for v0, and we need to evaluate all of these integrals. And these calculations can get pretty crazy, so most of the time we have to do it numerically, and the result is really cool. So we end up with these eigenfunctions, and this. So for example, this is a spherical octant. It's an equilateral triangle on a sphere. The angles of an equilateral triangle are right angles, just how the geometry works out. So it's the resulting eigenfunctions are different than just evaluating it on an equilateral triangle on a plane. But in this video, you can go back, you can compare how these eigenfunctions, you can compare them with those of the equilateral triangle. Here we have a spherical sextant. It's a square on a sphere, and these resulting eigenfunctions are very similar to those of a rectangle on a plane. Here are the eigenfunctions on a half sphere, very similar to the eigenfunctions on a circle. So I don't have time to share more, but more essentially, as I've extended this expansion method from just planar regions to more abstract regions, I found that this could be very useful for various eigenvalue problems. And like I said, all of the Laplacian and the Laplace-Beltrami operator, they're very, very common in a lot of physical problems. And on kind of a tangent, I just wanted to point this out. So a lot of the research behind these eigenvalue problems is looking into the various distribution of the spacings between the eigenvalues and how they correspond to other known distributions. One of which is in random matrix theory, the distribution of eigenvalues of certain different types of matrices. And on the other hand, research in Riemann zeta function, in the zeros of the Riemann zeta function, they find that the distribution of the spacings of these zeros also corresponds to these random matrix distributions. And so one area of interesting research is finding this connection between these quantum mechanical systems and the Riemann zeta function, which to me is crazy, bridging this gap between physical problems and number theory and analysis and pure math. These different ideas all come together, and I find it really fascinating. And so just as far as other areas of possible research, that's one, and another is just exploring more known eigenfunctions and embedding our domains, arbitrary domains, in domains of known eigenfunctions, and applying this method to domains of higher dimension. And one other area that I find really fascinating is the inverse problem. So there's a famous problem, can you hear the shape of a drum? And that's essentially, given some planar region, some unknown planar region with known eigenvalues, can one determine the shape of that region, just only knowing the eigenvalues? And that's been solved for planes. But to explore more specific domains, like, for example, it's known that given the eigenvalues of a unknown triangle, one can then determine the dimensions of that triangle. And so it would be interesting to look into more research on, is that true for spherical triangles or other things? And so there's many possible extensions, further research that can be done on this topic. And that's all I have to share today. And I appreciate everyone that's attending this conference. And I hope everybody stays safe. And that's all. Thanks.